infinity stuff that makes people go nuts. Let's see if we can make us go nuts.
Thank you for the organizers for the invitation. The talk is going to be about infinities. This is part of what my research is about. Although I decided to make it a talk designed for a general audience, more towards student understanding, and so I'll try to limit the actual heavy load of knowing stuff. Now, it's going to be up to you to go nuts based on this information, but actually I will show that in history, during history, people who touched questions involving infinity had a tendency to go nuts, literally. People ended up dying in mental institutions who were involved in this business. Now, the first guy, and I want to talk about the Greeks first, because everything meaningful in math started with the Greeks. And in particular, this guy, Zeno of Elea, we are talking about 5th century BC, so like 2,500 years ago, a long time ago. And that was so amazing about the ancient Greeks that they still, that long ago, they were talking about very modern way of thinking. Very modern questions were asked, and some of the answers are so profound that we still use the same arguments that they came up with. But it turns out that they had basically no understanding of what infinity is, and they thought they came up with all kinds of paradoxes. Paradox is you can view as a result of reasoning or logic that defy our experience, and Zeno was famous for that. He allegedly had like 40 of these paradoxes. He came up with these paradoxes. We have no record of any of his work. We mostly know about what he did and what he said from other peoples like Plato and Aristotle. You know, these are these other great philosophers who mentioned his name. One of his paradoxes, and probably one of the most famous ones, is about Achilles and the tortoise. Achilles was supposed to be this fast guy, very fast. Tortoise is a sea turtle, not so fast. But nobody remembers Achilles anymore, and we don't have tortoises that much here, so let me change it to a paradox of Carl Lewis and the turtle. This also tells you when was the first time I talked about this topic. It was when Carl Lewis was still active, I guess, and one of the fastest guys on Earth. Everybody knows the turtle. What is the deal? Since Carl Lewis is so fast, and the turtle is not so fast, Carl Lewis is gracious enough to give the turtle a head start. Let's say a little head start for the turtle, and because he is confident that he's going to catch up with the turtle, you know, like immediately really. Yeah, but it will still take time for Carl Lewis to reach the original position of the turtle. And during the time, the turtle is going, you know, it's slow, but it's going to move. So the turtle is going to be there, and the Carl Lewis is still going to be behind the turtle. And then again, a little time elapses while this distance is covered. The turtle is still going to be ahead of Carl Lewis. Now, and so on. There is no way that Carl Lewis is going to catch up with the turtle, because no matter how small the distance between them is, it still will take some time to catch up with the turtle to that level, and during the time, the turtle is going to be moving a little bit ahead of it. This is the classical Greek thinking. Since it takes infinitely many steps, there's just no way to finish it. There's no way to catch up with the turtle, which is clearly defying our experience. Carl Lewis is going to catch the turtle and going to win the race. So what's happening? Some kind of an infinity is going on. I cannot finish this argument because I would have to say and so on and on and on. But no matter what, there is always this discrepancy there. Another argument that the other paradox of Zeno is the so-called arrow paradox, which pretty much goes the same way. The argument says that if you shoot an arrow and there is this target at the end, you will never hit the target. Because in order for the arrow to hit the target, it has to cover half the distance. But it's still not there, right? Then it still has to cover half of the distance, still not there. and then half of the half of the half, and the half of the half of the half, and so on. It never reaches the thing, because it takes infinitely many steps. And how can it reach? Well, evidently it reaches it, so something is going on. But for Zeno, these kind of thinking, these kind of arguments were designed to show that basically what we think is a common sense is not so much, especially if you have these thought experiments involving infinitely many steps. Yeah, but let's go back to that original example, and just to make some assumptions so that we can actually calculate stuff with our modern understanding. Let's assume that the head start is about 10 yards. And let's assume, and it's probably definitely more than this, but just for the sake of the argument, let's assume that Carlos is 10 times faster than the turtle. Which means that if you start with the original head start, no matter what distance you are having, the turtle is going to cover the distance over 10, on the 10th of the distance that Carlos has to cover. So the next distance that we are talking about is going to be 10 times 0.1, still a distance, and so on. Then you have to divide that distance by 10 to realize what is the next place which Carlos has to catch up with. Dividing by 1 basically is like squaring 0.1. And you can see this pattern now. You know, in the next step, you would have to have the little distance that would come out here would be 10 times 0.1 cubed and so on. So the question is, what can we say about the sum of these distances? Because that's the real question. The real question is those 3 dots. 3 dots indicate that keep adding those things that you end up with having tiny ones probably, but keep adding them, and because you have to add, just by the nature of the argument, infinitely many little numbers, you will never get there. I can actually generate a general formula what those little distances would look like, since you are raising 0.1 to higher and higher powers. So this is the question. Or more generally, we can ask this question not for 10 and 0.1, but for any number, the first initial term, and then this other number q for quotient, that you keep raising to higher and higher powers. Is it possible, is it meaningful even to add the infinite many numbers? Now the Greeks had no way of doing this. By the way, the Greeks would never write this. They had no algebra. Algebra is a very modern invention. We're talking about 9th century AD or so, when algebra, everything, they spelled out everything. Mathematical ideas in the ancient Greeks looked like a novel, and everything was spelled out. There was no way for them to say anything like this, even if they had the idea how to add infinitely many pieces. Well, we have calculus now, since Newton and Leibniz and 17th century. And this is a calculus, maybe it depends on the school, I guess, or what is covered in calculus. Maybe not calculus 1, but calculus 2 or 3. This is a classical question, and it's a very simple thing, especially if you develop the notion of a limit. It's just a single, very simple limit to calculate, and you will end up with that result. Not always, but A can be anything, but if Q is small, in absolute value smaller than 1, then this is just summable. You can sum those things, and you get a finite number. Infinitely many things together, no problem, if you know the mechanism, if you know the tools how to handle this thing, and you have the math behind it. We had to wait about 2,000 years after him, but now we have it. So let's go back to the original question. So what is this? This should be based on that formula. Remember, our A is 10, our Q is 0.1, so this has to be the answer there. If you do a little arithmetic there, you end up with a number which tells us exactly, which is a finite place, exactly where Carlos catches up with the turtle, and we have our original normal experience. There is no paradox here. There is no paradox that defies our experience, just the math was missing. And the same thing would happen with that arrow. You would just add those little pieces that you are adding there, and the sum of those little pieces is going to be, this is a so-called geometric series, by the way. It will be a special geometric series, and the sum of the geometric series turns out to be exactly the distance that needs to be covered for the arrow to hit the target, and everything is just fine. The Greeks were not complete losers as far as infinities were concerned, though. Although they didn't know it. We know it now because we just know what their arguments were. Archimedes in particular is attributed to finding the area of the circle. Everybody knows it, right? A equals pi r squared is the area of the circle. Yeah, but have you ever thought about how substantially non-trivial this formula is? Or more importantly, have you ever thought or seen an argument which would tell you or prove to you that that must be the area of the circle? Now, why is it so extraordinary? What is pi? And I don't care about 3.14 or not, which is, by the way, not, because 3.14 is just an approximation of pi. But pi, when my daughter was elementary school, I wanted to make her understand what pi really is. So I told her, find all kinds of circular things, get a little thread, measure the circumference of the circle, and then measure the diameter of the circle, and keep dividing. Find all kinds of circular shapes. And within a couple of minutes, she said, "Oh, this is the same thing. The same number comes up." Yeah, because that is exactly what pi is. Pi is defined as the ratio between any circle circumference over its diameter. No, but therefore pi must be a linear thing. That's about a one-dimensional thing. You are measuring distance. And another distance, you divide two distances and you get pi. So how does that show up in an area formula? That's not trivial. To get that formula, I mean, using integration, using calculus 2 material, this is a straightforward, and that's actually pretty much the only modern way of getting the area of the circle, unless you want to do some simpler arguments. But even the simple argument has to invoke the notion of the limit, which they had no idea about. But Archimedes had a very good intuition. He didn't go for the area of the circle like that. What he ended up doing, he ended up looking at the inserted polygons that he can, regular polygons, and the area of the polygons he calculated from inside and from outside. And then he realized that if he keeps refining those polygons, that the areas coincide, and they must coincide with the area of the circle. But by doing that, what does it mean refining? Keep putting there finer and finer polygons, more and more vertices. I mean, but no matter how fine you are, if you stop anywhere, it's just going to be an approximation. What he had to have an intuition for is that this thing can go on, and basically this idea going ad infinitum will give you the right thing. The proof I'm going to show you here is not his, but it gives you the same understanding. Maybe this is the, maybe you already seen this argument, but it gives a good representation of what we are talking about. And Archimedes could have come up with the same argument as well. Let's take a circle, random circle of radius r, cut it into 4 pieces, quarter circles, and what we are going to do, we are going to rearrange those little quarters, like that. That little dotted curve, dotted line is coming from the radius, so that's the radius, that distance there. What are these two arcs together? They were formed from 2 quarter arcs, so they must be the half arcs, or semicircle length. We know what is the circumference is 2 pi r. Just solve it for C, this one. So the side, the two arcs must altogether be pi r. The length must be pi r. Why don't we cut it further? Let's refine our thinking, and let's do the same thing. Let's arrange these guys exact up and down, up and down. I mean, nothing changed as far as the r is. It's the same r. The little pizza segments have the same radius. The arcs, and the pizzas are narrow now, narrower, but you have 4/8 of these arcs. So that still gives you the pi r, because together they always give you the whole circle. And another, and I'll stop here because I got bored calculating all these coordinates. But look at that. You should see the pattern now. It's still r. Those guys together will still give you a pi r. And what you can say, well, it has a tendency, that shape that you, after rearranging, it looks like a rectangle eventually. It's not a rectangle. It's definitely not a straight. These are arcs here. This is not perpendicular to the other side. But if you do it, and if you refine it further enough, never stopping, and that's the thing, never stopping. How can you not stop? I mean, your whole existence is finite. Not stopping would mean infinitely many steps. That's where the limit, notion of the limit comes in. But I already showed you that having an infinite process, adding infinite many things, will not cause a little bit problem, a big problem, because you can still come up with this idea. It looks like, indeed, these shapes, if you refine these ideas far enough, will kind of produce a rectangle for you with one side r, the other side length, pi r, width r. So the area must be pi r. This is a reasonable assumption, at least. That's how you can get your pi r squared. And that's a totally legitimate argument, especially again if you employ the idea of a limit. Okay, let's jump 2,000 years or so, more even. So this guy, Georg Cantor, who is definitely the founder of modern set theory, hate it or love it. I know that there were these programs, I don't know if it's still there in elementary schools, that we have to teach everything through sets and stuff. I remember when I was in high school, back in Czechoslovakia, it was kind of the new idea that, you know, this is such a beautiful generalizing idea that we have to expose everybody as soon as possible to that. It was a complete disaster. I mean, this is a very beautiful mathematical idea, but you have to develop a little bit of understanding to sell it. But he is the culprit. By the way, going back to those two Greeks I mentioned, Zeno of Ilia allegedly was killed because he didn't like the tyrant of Ilia. There was such a guy, the tyrant of Ilia, and he tried to kill him. He didn't succeed. The tyrant succeeded. So he died quite drastically. The other guy, the circle guy, Archimedes, he was a famous guy. He did all kinds of things in the sciences, inventor, all kinds of stuff. He was killed by a Roman soldier because Archimedes refused to go with him because he was working on a math problem, and the Roman soldier didn't like it. So again, a drastic end. Cantor didn't die that drastically, but he died in a mental institution, trying to solve his own problems and all paradoxes. Divorced, broke, in a mental institution. Not a good ending either. That's why the title. What is Cantor said? One of his, it's my understanding that he's in one of his publications, he just mentioned it as a nice thought process. He didn't really dwell on it, but it's an unbelievable construction, and it is very useful in modern math. Let's do the following. Let's start with an closed interval 0, 1, and let's cut the middle third out of it. So we end up with two other intervals of equal length, third of the original one. Let's keep doing that. Let's keep cutting out the middle third. Actually, it's called the middle third set. That's why the title. And we get 4 new intervals now, these. And cut the middle third of those 4 intervals and get these intervals. And again, don't stop, ever. Keep continuing. The question is, if we keep cutting these guys out, are we going to get anything? Maybe with any finite stage, we always leave something. I mean, actually the majority is still left there because we're just cutting the middle third. But at the end, if you don't stop cutting these things, are you going to cut everything? Well, let's see. Let's measure what we cut out. Let's measure what we cut out. In the first step, we cut out from the unit length a third. So this is the length of the sum of those two guys. Then in the next step, we cut out a 2 times the third of a third. So the size of the cutout in the next step is this big. And so on. In the next step, you cut out 4 of the thirds of the 9th. So you can write it like this. There seems to be a pattern. At every stage, let's say on n stage, based on these numbers, we are cutting out 2 to the n over 1 over 3 to the n plus 1, it's always the bigger one, with the 3. But here is the thing. Keep doing it. If you do that, you can still call for the formula that I already quoted earlier. This formula is still there. The question is, because it seems to be, yeah, it's subtraction, but I can always pull out the minus if I don't like the minus, which I will do in a second. But the rest is about powers of numbers. And the numbers are actually not that bad. It's 1 over 3, some powers of 1 over 3. That's a small number. And even 2 over 3 raised to higher power would be a small number. And actually, you can rewrite the whole thing in those terms. So what I'm going to do here, what you see here, I just pulled out the minus from everywhere I could. And I peeled off one of these 1/3 from every power. Why? Because I want to have a common nth power in every term. And if you do that, this is exactly what this symbol is about. And the stuff in parentheses follows that boxed formula, with a equals 1/3 and q equals 2/3. And for those numbers, that formula works just fine. So this should be the answer. This should be the length of the remaining interval, or the remaining whatever. It's not going to be an interval. It's going to be the counter set what's left at the end. And again, if you do the math, 1/3 over 1/3 is still 1. Exactly like the original length. So look at this. At the end, you remove everything. The size of the remaining interval, or remaining set, is 0. And this is just fine. All this argument is fine as soon as we accept this one, but this is standard math now, standard calculus stuff. So it looks like there's nothing what's left. Yeah, but that's not true. Think about 0. We never touch 0. No matter what you do, no matter how far you go with this argument, you will never remove 0. 0 is just going to be on the left side of these intervals, and that is not. 0 is always going to be in. 1 is always going to be in. Every single stage, infinitely many times you do it or not, is going to be always there. Every one of these cutting intervals, cutting numbers will be there. 1/3, this is just going to be there. You are always removing the middle part after all. Well, so it means, it looks like all these fractions that I drew, and even further you go, those cutting angles, they will always be part of the final product, whatever it is. So it's definitely not empty. It has a 0 measure, whatever that means, but it's definitely not empty. But the truth is actually even more drastic, because we can do the following. Why don't we code what we just did? I'll use a 0 whenever I want to identify the left interval that is left after removing the middle part, and I'm going to code the interval which is on the right by 1. And those are the two numbers only that I need in this argument, because it's always, wherever I'm at, there's always 2 intervals left. So there will be a 0 here, 1 here, a 0 here, 1 here. A 0 here, 1, 0, 1. So with those intervals, I can code every single one of these steps. Like this. There is no choice in the first step, because it's just one interval, so I'm just going to call it a 0. And after that, this left-right argument would work. Now, let's think about the following. If you take the 0, let's build numbers using these digits 0 and 1. 0 is going to be the first one, so I'm going to use it as if it was the whole part. And after that, because there are options here, it can be 0 and 1, 0 point, and whatever follows based on those choices. If I keep using zeros on this part, then these intervals will narrow and zoom into the 0. If you want to have a proof of this, you probably have to take some high-level course, which is like real analysis. I don't know how it's called here, analysis, advanced calculus. And there, the so-called nested interval principle is proved, which says if you take any closed intervals that are shrinking, the length of those intervals is zooming, there is always a single point in it. So you can think about these intervals that I'm labeling by zeros as basically like a road map, a path, which leads to a single guy at the end. A single guy will be the end of the road of these zeros, which is 0 exactly. If you want to take a look at the first one and these guys here, they will go down to 1. You just have to keep using 1 as for the right thing. So that basically, these guys will collapse into a single number, which is our 1. But we can also use a random array of numbers. You can take 0, then 1, then 0, and again this 1, and then keep taking 1s. So you will go like this, which means that you will probably end up, no, you will exactly end up with the number that was this dividing point, which if you go back to my original script is 7/9. So what I'm doing here, I'm coding every single road that I can build in this so-called counter set. And the end of the road is a member of the counter set. The road represents the element of the counter set. And I just gave you some numbers here, which are dividing numbers, but here is the thing. These are going to be nice collections. Whenever you have a pattern, whenever these numbers are periodic, that's what this is like. Like in normal case, if you have a 1/3, which is 0.3333, but the 3 is repeating and it's predictable. You know exactly when is the next term. That's the sign of a rational number. That's how fractions are designed. Pi is not rational, because if you're trying to get the pi's decimal expansion, you will never know what is the next number, unless you calculate it. There is no predictability behind irrational numbers. And you can do the same thing. What if you take the 0, you have no choice there, and then after that you have a random collection of zeros and ones. There's all kinds of possibilities there. And no matter what 0 and 1 collection, no matter what sequence of zeros and ones you take, that will produce a path for you. A path of closed intervals. Those closed intervals will always result in something. That's the idea behind the nested interval principle. So any sequence of these zeros and ones will produce a member of the counter set. And conversely, if you are in the counter set, a road will lead to you. What road? A road coded through zeros and ones. So it looks like, and that's where I'm heading, that there is a so-called one-to-one correspondence between the counter set. Every point in the counter set can be associated with a sequence of zeros and ones, or more specifically, we said those zeros and ones will look like this, where those A's are 0 or 1. But if you don't allow any other digits but zeros and 1, then you are basically talking about a number of base 2. Computer scientists love these numbers. Usually those numbers in computer science are finite and an integer. And you learn that any number can be expressed in any base, in particular in base 2. But actually it can go the other way around, like decimal. Why our numbers are decimal numbers? Because we have 10 fingers. The numbers didn't know that. Numbers don't know how many fingers people have. Numbers are numbers. So sometimes numbers want to be reminded that they can be expressed in base 2, 3, 7. But if that's the case, then it looks like every single number between 0 and 1, or any real number, can be expressed not just in base 10, decimal, but base 2. And this is exactly how they would look like. This is exactly how they would look like in the interval 0, 1 closed. Every number can be represented by sequences like that. Not called decimal, but binary sequences. Yeah, but that's really weird, because we just showed that the counter set, which has 0 measure, has exactly the same size, one way or the other, because there is a one-to-one correspondence, as the original huge thing. That's the original huge thing. And this one-to-one correspondence, isn't that how we count, really? When I want to find out how many people are in this room, what would I do? I would say 1, 2, 3. I'm setting up a one-to-one correspondence between a certain group of integers, or natural numbers, and everybody here. I'm labeling. I'm setting up one-to-one. Setting up one-to-one correspondences is what counting means. All I'm doing, I'm pressing this argument a little bit further for infinite sets. I mean, it's the same idea, so why not to apply it to infinite sets? This seems to be. So in that case, what I just realized is that the counter set has exactly as many elements as everybody to begin with, although I removed everything, really. That is a very typical thing whenever you work in infinite collections. There is only one conclusion you can take. The counter set is a big nothing. Okay, let's go back, and this is the end of my talk because I want to mention some interesting results, and this is where the whole theory of sets erupted, and it's now one of the most hardest and but well-established parts of mathematics because we understand what's happening. Cantor didn't. If this happens, what I just said, that between two sets, call them X and Y, there is a one-to-one correspondence, there is some kind of a one-to-one correspondence possible, we will say that those two sets have the same cardinality. We will not say that they have the same number of elements, because that smells finite. But cardinality is the official term for the size of a set, which is possibly infinite. This would be the notation. It looks like an absolute value, but it's not. It's the cardinality of those two sets. The smallest infinite set that you can imagine is the set of all the naturals. Is that, by the way, infinite? How do we know it's infinite? Because no matter where you are, you can get the next one. How? Just by adding 1. So you will never finish counting the natural numbers because there is always this next one. That's exactly what infinite is. Move on and on and on, those 3 dots. So what is the cardinality of the naturals compared to the cardinality of all the integers? Z, why Z the integers? Because Z is Zahlen in German. Cantor was German. We still use his notation for the integers. I mean, it's the same cardinality. It's a very simple argument, but this is totally counterintuitive. How can a bigger set have the same cardinality as the smaller one? Actually, it's not that bad once you survive the counter set, because that's exactly what happened there. But this is even worse here. If you take all the fractions, all the rational numbers, I mean, they are everywhere. You learn it in advanced calculus that the rationals are so-called dense. Any interval you take, small or large, you will be able to find a rational number there. And yet, you have exactly as many of them as the naturals. So you can think of the moment, yeah, come on. We are talking about infinite sets. There must be just infinite many of them, and that's what we are talking about. Not really. If you take the next collection of infinite things, all the real numbers, it's not just that infinite. They are markedly bigger than the natural numbers. You can prove, and it's a very simple argument. Cantor found that argument. The Cantor diagonalization principle can show you that there are more real numbers than naturals. There are infinities, not just one. There are several infinities there. Some other examples. If you take the 0, 1 open interval, just add one guy. Not surprising, I guess now, because of the Cantor set. It has to be the same cardinality. Add 2 of them, same cardinality. Add everybody, same cardinality. I could have put the whole plane. The whole plane has exactly as many points as this little interval 0, 1. Again, quite simple argument. But here is the real shocker, and this is why this is and this is pretty much the end of it, end of my talk. You can take any set X, of infinite or not, and then you can take all the subsets. So let's say that X is the naturals, and those are some natural numbers, and you come up with this P of X, the so-called power set. Just collect a bunch of natural numbers in all possible ways. And you create a new set with them. That will have a cardinality too, a certain size. The power set is always bigger than the original one. So if you start with the naturals, the power set is going to be a bigger cardinality. Okay, so take the power set of the power set. That is going to be even bigger. And this is never going to end. There are infinitely many infinities. One last thing. Okay, so there is a gap here, there's a slack here. There's a cardinality of the naturals. People in math eventually run out of symbols, so you just get anything you can get, like the first letter of the Hebrew alphabet, Aleph. That's what they use to indicate the cardinality of the naturals. And what about the next cardinality? There must be a next cardinality because there is a bigger one. So is there a cardinality which is bigger than Aleph? No, but the first one in the line. They denote it by Aleph1. But the first natural thing that comes to mind would be the cardinality of the reals. Actually, that was a big question for a long time. It's the so-called continuum hypothesis. Is it true that Aleph1 is that? The cardinality of the reals is that next cardinality? And the answer is totally mind-boggling, because the answer is, it depends. The answer is not yes and no. This question is not decidable within your normal axioms of set theory. If you deny it, and you attach to other axioms, you can build a system that is just fine. If you keep it and you attach to the other axioms of the system, you are still going to get a good logical framework. The two frameworks will probably produce different results though. And it is completely understood and fine as far as we can guard our conclusions. So all I'm saying is that this is a mind-boggling and fascinating topic. A lot of people went nuts, but some survived, and that's why we know all this. Thank you.
Do you have any questions for the speaker?
Yeah.
So, given that we know this, is it okay that I still get a headache whenever I think of the...
That's the normal thing.
Okay.
That's the natural.
Okay, let's do the speaker again.